Hi all, good morning. I am Swathi Gowda. I am working at Bosch for 2 years now. I have a total of 6 years experience in embedded systems and I am from India, as you can see. Today I am not here to speak about the success, I am here to speak about the failures. The failures that usually kind of frustrates us, confuses us, and eventually it will make you learn more than anything else. So, in embedded world, we call them as bugs. The bugs that I'm going to talk here is not the insects that are around us. No, it's the tiny little stubborns that doesn't behave in the code as expected. So, as it said, sorry. So, as it said, uh, mistakes are the best teachers. In embedded world, I like to reframe that as bugs are often our best teachers because they show us what correct code doesn't. They usually create us the opportunity to learn outside of the box. So before aligning into this bugs word, let me give an explanation of what embedded systems are like. So embedded systems are nothing but are not like a regular software. It's not completely about the software. They live in the real world, like washing machine at your home to the ABS system in your car, and also the coffee machine that you use is an embedded system. To state in technical terms, they are the combination of hardwares and softwares designed to do one dedicated functionality. For example, if you take the micro oven at your house, their functionality is to deal with food alone, and they don't have to give you any 3D prints. So embedded software usually have a dedicated functionality. And we deal with the real-time constraints. For example, if a car crash happens and your airbag is taking extra zero point 0.5 milliseconds to deploy, the delay is very catastrophic. So we deal with the real-time constraint and the timing is very strict and critical. And we deal with the less resources. Unlike the big computers, which deal with the gigabytes of memory, we deal with the kilobytes of memory. And also, we work with the less power in the sense, the watches that we wear, we usually expect it should run for 2 to 3 days with a tiny battery. So that is the kind of power that we usually work with. And low cost, I don't say it's only restricted to embedded system, it's all over. It's preferable to go for a low cost. So we have this constraints of hardware dependency, real timing constraints, and less resources. Imagine if there is a bug in this kind of system. That's where the things get really interesting. So the bugs that I'm going to talk about today is not the missing semicolons in the code. They are like everything in the code is perfectly fine, and yet the system will fail. It's like debugging them is like performing a surgery in the dark. Why do we feel that? Let's explore that. So the first thing is the observer effect. So when something is not going in the code, the first thing we try to see is like observe what is in the code and see where it is going wrong. So as usual, we'll try to, in embedded system, observing might create the problem or it might solve the problem. We don't know. We are dealing with something what is not visible. For example, if you're trying to add a print statement in the code, it might create a 0.1 millisecond delay, which will solve the existing problem, or it might, it might create a new problem. So this is very challenging here. And as I said, we deal with the real timing constraints. So the timing constraint is not in minutes, it's not in seconds, it's in milliseconds. So debugging with that such precision is a very difficult task. And next thing is black box problem. Embedded systems, most of the embedded systems are headless. We don't have any monitor saying that there's something wrong or it will not even give us any error. It's simply an indication of some LED stops blinking or it might be some smoke in the system. So it's not easy to find out what is happening in the system. And the next thing is, since we are dealing with hardware and software both, so it's very confusing. Where is the problem actually? Is it the hardware or is it the software? If neither of them, the environment can influence the system. It's like a loose wire in the system or overheating or any noise in the system can also look like an embedded system. So now, can also look like a bug, software bug. So now the problem is, now the question is, how do we overcome these issues? So what we do, instead of fighting the system, we try to adapt how we observe the system. To overcome the observer effect, we try to avoid the disturbances or reduce the disturbances by using a hardware debuggers. We call it as JTAG. So this will allow us to scan through the code while the system is running. So you know what is happening inside the system when the system is actually running without disturbing that. The next thing is the real-time constants. To see what is happening at each millisecond, we have some of the tools like oscilloscopes and time tracing tools, which will help us to deal with real-timing constraints. The next thing is we try to make the system talk to us. Like I said, we are using some hardware debuggers to know what is happening in the system even when it is running. This will help with us. And software hardware ambiguity, we try to go step by step by isolating one by one, whether the problem is in hardware or is it in the software. So now we have the tools, we have the techniques, and we have the mindset. And sometimes still nothing makes sense. So today I am going to explain one of those bugs. So once I worked with a system where everything was working perfectly fine, except for one functionality. So in code, everything was proper, the logic was up to the mark, and yet this one functionality was not working. There was no response and no clues and no crashes. So, okay, this bug made completely no sense to us. So let me explain what is the functionality which was not working. It is simply that there was two modes, the update mode and the normal mode. Update mode is more like a bootloader, if you are aware. There should be a transition from this update mode to the normal mode. So update mode is basically where you write the code into the memory, and normal mode is like when you start the system, it will go through the normal mode and it will try to read the code that you have written in the memory and run the code. So when we are testing this, we have two manual method. One is a reset method, another one is a diagnostic method. I don't want to go too technical here, so I will just name them as request A method and request B method. So request A, the transition was perfect, it gave us positive response, and everything was fine. With request B, there was no response, and the transition didn't happen. It was kind of a silent failures. So as the software engineers, the first thing we try to debug the system. So first thing, we try to debug the code line by line, see where is there any problem in the code. And also we verified the timing, since timing is very important to us. And we also, since we didn't get any response, we couldn't find any traces of errors in the logs. And we also verified hardware and checked there was no fault in the hardware. And we tried to reflash the code multiple times. And yet, we couldn't find the problem. So about debugging, it's like instead of solving the issue, it is the main challenge is finding where is the issue is the biggest challenge to us. So after debugging for a week, we realized that we had flashed a wrong version of code to the system earlier. And even after flashing a correct version of the code to it, the memory was not completely cleared. That means like you're writing on the whiteboard without previously erasing what was there. So that data interfered with the execution of this functionality alone because this functionality was dealing with the memory. So, what we learned from this here, sometimes the system is not wrong. It's just that you're not starting with a clean system. So always make sure to erase the system to avoid any hidden memory issues. So what we this actually gave us the experience that you cannot simply trust the clean-looking system because you cannot simply trust the clean-looking system because sometimes the problem is what you don't see is the actual problem here. But memory is not the only thing that will fool us. Timing can be even more worse. So for that, I can explain you with one more example. So I think every one of us had been in this kind of situation where when the system is not working, whether we ask or the first thing we try to do is a reset. So the question is how it works. So let me explain you in embedded terms. This could be one of the solution, but I will not state this is the only solution. This could be one of the solution. So let me explain this with one example. So you wake up in the morning, you power on the coffee machine, and you press the button for coffee. The coffee machine makes a weird sound. It might even throw some errors, but there's no coffee. So our immediate instinct will try to reset and see what's wrong. And immediately the coffee machine starts working. So it's the same software, and it's the same hardware. We didn't change anything except pressing the reset button, but there's a different behavior. How does this happen? So what's really happening? When you power on the system, the microcontroller is powered on immediately while the sensors are not yet ready. That means my microcontroller assumes that they are ready and try to communicate with them while the sensors are still like initializing in that phase. So what happens when you reset? The system is already powered on and sensors are already ready. And microcontroller, when they try to communicate, the sensor will respond to it, and now your coffee machine works all right. So the problem is not the logic here, it's the timing issue. Here the system assumed that everything is ready and I can communicate, but no, it was not. The assumption was wrong here. So the most important thing is if the reset is solving your problem, that does not mean the problem is resolved. It means there might be some issues that is not yet found. So so far we saw the bugs with the memory and the bugs with the timing. In both the cases, the logic was perfectly fine, and yet your system failed. So how do we debug this kind of problems? So the first thing that comes to our mind when we think about debugging is about the tools. For observability, we had the locks and trace, and for signal tracing, we had oscilloscopes. For inspection, as I said, debuggers, and to refer, we had a data sheets and specification. Yes, these are important. But tools won't solve your problem, or tools won't debug the bugs. People does. So even you might have even you have a better tools with you, and yet you can be stuck for days debugging. It's not because visibility is not the problem here. It's in the understanding. In both the cases, we had all the tools, we had all the logs, and we almost verified everything, but yet we couldn't find the issues immediately. It's not because the tools failed, it's because our assumptions were wrong initially. So it's like debugging is not about collecting data. It's about asking good questions, like what am I changing here and how it is affecting the system, and can I reproduce it in variety of conditions? Like if it is working in one condition, is it working in other condition? There are chances that it can fail in other condition. And when I am debugging, we should also think about what am I assuming here? Is my assumption correct, or is my assumption wrong? We have to question that. And also, we have to make sure, since the embedded systems is more about timing, we have to make sure that the timing and the sequence, is it the same as what we are thinking here? And so it's debugging becomes way easier if you have a known good system to compare. So tools, they will always try to, the tools will say what is happening in the system. They'll give you the data about what's happening inside the system, while the mindset will give why it's happening like that. So debugging is more about thinking in different way. So this taught us, the bugs, what we saw so far taught us that bugs are not random, they are clues. If reset fixes it, you can imagine timing could be some of the issue. And what you see is not exactly what is happening. There might be some hidden issues that you are not aware of. And you can reproduce it, you can compare it, and you have to question your assumptions. So tools will show the signals, while the mindset will try to give the meaning for it. So in embedded systems, even when the logic was correct, the system failed. So what we realized that is embedded system is not only about logic and codes, it's about timing, state, and the interaction. So in this world, bugs obviously become our best teachers, not because they break the system, because they teach us what we didn't initially think or what we didn't initially understand. So, yeah, that's all. Thanks.